Okay, so another day, uh, and we're continuing the Cranelift series. So today, I think um, I've got a topic where we can only spend a couple of minutes. It's mostly something that I've been meaning to sort of put in order for myself. One, because this is Cranelift is a project that's pretty big, and there's way too much happening in many parts. Sort of organizing uh, at least the mental map is very important, at least to me. So, what I wanted to talk about today was the various implementation in Cranelift. What sort of design choices were made specifically, and also we'll talk about you know how you can go about putting a backend, at least a very very high level overview. So those two things are what I'd basically like to talk about. It's just going to be something that you know, where we explore the Cranelift code base and look at some things that are very interesting. So to start off, let me quickly get to the point. So there is this. I've made, I've put pretty much what I call essential Cranelift data structures. Everything is essential. Obviously, that's why it's part of the Cranelift implementation. But at least the way what I mean by essential over here is things that you need to know, or if you get a good idea of what it is, you'll be able to sort of mentally map things in your mind. So there's some things called Cranelift entities, and then Cranelift instruction formats and data. Then the file specific types that we talked about. We've got two videos on that, so you can look at that. But types pertaining to that and how that's important. And then the backend. All right. So once we have these four, then we can pretty much put together a picture to say, okay, here's how I think you would go about putting a backend. So um, to sort of quickly get started, the best place to sort of start is the documentation. And this is the documentation for Cranelift. By the way, there's, you know, if you go to like the public documentation, which is documentation that is available on the web, which is this stuff, this is good, but this is documentation that's pulled from crates.io. So, you know, you could be missing a couple of things, like, for example, private items, etc. Um, and I would recommend when you're working with such a large project to actually pull in documentation that is a lot more of the documentation that you want rather than you actually having to read through code comments. So here you see that Cranelift documentation, although there are private items that need not be part of the public docs, you can actually read them over here. Uh, this is nothing to do with Cranelift. This is just something that you can always do with any project. But I just thought, I'll talk about that. So that's one. And the second thing is, so if you look at the Cranelift project, it's sort of well organized and all of that stuff. But let's actually focus on the first part, which is the Cranelift entities part. So if you jump into this, you will see that Cranelift uh, is a little different. I mean, if we were comparing it with LLVM, um, it's, for that matter, if you're comparing it with any compiler framework or a backend code generator, any other one, that is, you'd see that the implementation or the design choices that they've made are a little different. So over here, the first thing that you need to keep in mind is, well, if you're talking about compiling stuff, you're obviously going to be compiling, whatever source code you've written into uh, machine instructions. And we've already talked about the various intermediate representations that we'd go through to get to that point. In here, when we talk about Cranelift entities, you can think of the scenario as, let's say, we want to refer to a function and the components that make up a function. Things like okay, a function could have, blocks of code in there, and those blocks of code could be sort of related to each other. What we'd call a control flow graph, or in Cranelift's case, you can also call it a data flow graph, which is another important data structure. But effectively, you can think of what Cranelift is doing is it's going to be taking in Cranelift IR, which is in the form of uh, this graph form, and it's going to output machine instructions. So in here, Cranelift will have those. You can just put a mental model together that you will have blocks, and those blocks are related to each other. That means you have a graph of them. And within each block, you'll have instructions, and those instructions themselves will be composed of, operands. So pretty much function, blocks, instructions, operands, and yeah. But the thing is, you'll have to, when you start picturing how you would represent Cranelift's IR, the one that we talked about in the previous videos, you would want to actually figure out, how you'd want to represent this. And that's where Cranelift's this entities module comes in. This is a way to sort of represent those entities. Entities here can be things like blocks, functions, instructions, operands, whatever it is. And that's kind of what I wanted to focus on, because the way this is, uh, I was trying to look for a very, I don't know, I just read the documentation a little while ago, I think. There was some documentation. I couldn't find it. But anyway, let me see if I can explain that as well as I can. So firstly, you're going to have something called the context, which is pretty much a data structure that's going to be around during a compilation, the entire compilation pipeline phase, that is. It holds the entire state of a compilation pipeline. What do we mean by that? I'll talk about that. And then you've got the function. The function in this case is basically the function that we're going to be compiling. If you remember, Cranelift compiles individual functions as a single unit of compilation within Cranelift is, you can call it a function. And then all those functions are going to be linked up, and all that stuff happens towards the end. And then there's this thing called entity references. Now, entity references are separate from the entities themselves. Obviously, there are references to entities, but you might think that it's probably a Rust reference of sort. No, it's not. It makes things very difficult if you simply use Rust references. So the design choice that was made over here is you basically take something like a simple U32 and wrap it in a struct, and then you use that to identify the various entities, the ones that I talked about, things like blocks, instructions, stacks, logs, etc., like I've mentioned over here. And why are we calling these entity references? So the moment you see that the entity reference is an actual reference to an entity, you could probably use that reference as a key inside of a map. And that's where this concept of primary and secondary maps come in, which is what is being mentioned over here. So yeah, enough talk about this. Let's actually go look at this. So basically, go into the Cranelift project, go into the entity implementation. You should be able to see everything over here. Mostly, I just want to go look at the main, the one that we were looking at, basically the documentation. Here's the actual implementation for it. Yeah. So much of the entity implementation is in a macro. We basically see entity implementation, where for each type of entity, whether it's a block, whether it's a function, whether it's an instruction or something else, you rather than do it, rather than have every multiple implementations for that. You can probably put that in the macro. That is one. And then there's this primary map. I wanted to sort of show a neat little example so that I don't have to delve into a whole lot of things. Let's see. Yeah, this will probably look a little abstract if you keep going through this. Let me do one thing. Yeah. See what I meant by a large project? You really have to keep finding a way. Where was that? Primary map. You know what? Screw it. Let me just go and find. Okay. To do. Yeah, great. So yes, you can start off by looking in the IR folder or module, where within CodeGen, IR basically contains the entire, whatever you wanted to do with. Somebody gave you some Cranelift IR, and you want to do something with it. Pretty much the entire implementation for that is in here. You have something called the DataFlowGraph, which I will talk about in a minute. But here you see some things like a secondary map, uh, B-tree maps, something that is standard. But then you see what's called a primary map, right? So let me just quickly jump into its implementation. The first thing that you should see is it's basically a vector, right? It's just a wrapper around the vec type and not much. But the fact that they've actually built a map without pretty much having to store the key, because phantom data is a type that it's compiled away. You don't really see that in the implementation, in the actual code that's generated. So the way these primary maps are actually implemented is that the entity references that we talked about are the actual keys that are used to sort of index as an index into the vec. And if you look at the documentation, that's kind of what it says as well. So these are array-based data structures. In this case, array-based is, a vector is sort of an array, except that it's a growable array. So the idea is that rather than using a standard map type implementation, which could potentially take up a little more space, you could do this using a densely packed data structure like a vector, where you'll use the key, but it's only available to you to compile time, and you'll be able to access, the different indexes in the vec to pull out the corresponding entity, right? Why would you want to do this? Because improve type safety. If you control the type of the entity reference, you're basically saying that this entity reference will only allow you to pull out or basically index into a block, a block map or a map that contains blocks, right? Then you can be rest assured that you can use that key for something else, right? There's no confusion about the meaning of the index over there. Rather, if you talk about indices when you're talking about a standard array, it's just 0, 1, 2, 3. Rather than that, you can do this. Smaller indices is the other one. I think this is primarily why you'd want to go with something like this. And additionally, also there's another point where if you think about compiler implementations, generally folks would like to use Arena generational arenas are what they're called. This is a concept that comes from entity component systems where what you would normally do is you've got, let's say you've got mm, you've got some memory. You've got, yeah, let's assume that you've got some contiguous memory over there, and you got to, and you've got, how do I put this? Yeah, you got like a vec. Let's assume that, and then you want to put some elements in there into that vec. Generally, what happens with compilers is that uh, some of the entities that you are working with are no longer useful, and you should sort of drop them. And then you'd probably want to reuse that space rather than extending or extending your rec or something like that to save on space. And then you end up using things like generational arenas, where you, apart from just an index for every element in the data structure, you'd also want to give it a generational index. And that's where generational indices also come in. But there's a lot of complexity in keeping all that state around, etc. So this is another design that the Cranelift team has chosen. And it's actually pretty easy to work with. Yeah, we worked with generational arenas. I'd say this is much simpler, and I think there's going to be less complications as you go forward. That's one way I can think of explaining that. Yeah, so that's the entity part. And now you can have entities that are, access to those entities. If you've got a string of entities that you want to use, you could use a primary map, a secondary map, which is basically a map that is associated with the primary map because you use the same keys in both of them. The secondary map gives you additional data that you want to store. And then there's a sparse map, an entity set, an entity list. All the stuff very similar. But the main key thing is that the design choice over here is that it's using this array-based data structure, not the generational arena type. Y gives you the type safety, it gives you, obviously, saves a lot of efficient use of your space in a compiler like this because it's an optimizing compiler. And one of its goals is also that it should be the fastest possible compilation time that it takes, not the code that's produced, the time it takes to compile stuff, because it's also used as a JIT compiler. Great. And then there's packed options, etc. Obviously, as I said, I don't want to dump into every single type. There's a boatload of them. Just want to talk about at least the main stuff. So yeah, what am I doing? Let me actually look at the first thing, the function type. Where is that? Yeah, it's an IR function, as usual. So if I go into function, this is your function type, and this is the function stencil. Basically, a function stencil tells you everything you need to know about a function. Signature, stack slots that are used in this function, the dynamic stack slot, the global values, blah, blah, blah. It also keeps holds on to a data flow graph. Now that we're already here, let's talk about that. But before that, there's a layout. So the layout defines the order and the number of blocks and instructions in a function, right? So yeah, we didn't talk about that. That's fine. So basically, this particular type pretty much gives you access to all these other, fields that it has. The layout is basically going to talk about the number of blocks and instructions in the function and the order, what is the sequence of those instructions, etc. That's what layout talks about. If you were to look at it, um, this is this is how it's laid out. So you say blocks, instructions, what's the first block, what's the last block, stuff like that. And in the secondary map, in the map that you're using, this is a secondary map, so there's probably a primary map somewhere. You should be able to, let's actually read this. The layout struct determines the layout of blocks and instructions in a function. It does not contain definitions of instructions or blocks, but it depends on the instruction and block entity references being defined elsewhere, right? So we're only talking about the order and the number with the layout. the definition of those block entities is somewhere else. We'll talk about where that is. And then, yeah, that's one. And then you've got the data flow graph. The data flow graph, in my view, is I think the main thing that you would want to look at. Uh, it's pretty much where everything gets done. So let's actually look at the, the doc switch. Uh, mhm. Yeah, so this is basically the local version of the docs with private items and everything that you need, all the features enabled, etc. All that stuff is done. You don't have to go running around. So yeah, function. Then we have that. Stencil data flow graph. Yeah. So yeah, you could directly jump to it because all of this is part of the IR implementation anyway. Yeah. So, but if you think about it, the data flow graph represents all instructions and basic blocks within a function, along with all of their the data flow dependencies. In fact, this is where, pretty much the entire implementation resides. So it's got the instructions, it's got the blocks, as you can see here, instructions and blocks. You can, if you want to look at them, you can look at them. Let me just go back. So if I was to look at them and say, what is an instruction? You'd see an instruction is just a map. Given a key, which is the instruction in this case, this is an entity reference, you would be able to get the instruction data back. What makes up the instruction data? Okay, I can't jump into it. I'll show you what that means. But this is, as you can see, it's an entity implementation. It's basically a number that's wrapped, a U32 number that's wrapped, that helps you create your own indices, which are typed. And what is the instruction data piece? That's a little more involved. You would pretty much have to jump into actually my Rust analyzer thing, because I've made some changes and broken Rust analyzer. It's not working, but I could jump into it. So if I was to go into the build repository and hey, where's my out folder? Oh yeah, sorry. So just pick one. Right. So here you'd be able to see under what's called opcodes, you should be able to see instruction data, right? This is your instruction data. So it basically captures Cranelift instructions or other instruction formats and the associated data with them. So each format, each instruction could be could have a certain format. That's an encoding format. And then we figured out using both the instruction format and the instruction data, you'd be able to figure out, what sort of instruction are you dealing with and how is that actually represented in Cranelift IR, and then how you can translate that to machine instructions, right? So yeah, that's the data flow graph. And one interesting thing over here is I don't think Cranelift uses what's called def use chains. This is a concept that you will hear in the compilers where, yeah, so basically in Cranelift, whenever you have values, they're probably SSA values that we discussed last time. Whenever you say that, okay, I've defined this SSA value here, which means I've written to that, yeah, I've instantiated an SSA value and I've written to that. And I want to know where it's used post the definition part. That's, usually there's a data structure around that keeps track of that and other sort of design choices, but I guess Cranelift doesn't do that. Cranelift pretty much uses the DataFlowGraph to figure that out. So that's another interesting choice. Yeah. And then we were talking about these two things. We were talking about instruction format and instruction data. So every Cranelift opcode, and I sort of went through this in the last stream as well. We talked about basically opcodes, right? So what are the Cranelift formats, or what formats is the Cranelift has Cranelift provided? Okay, so there is, so basically an atomic compare and swap, atomic read modify write, binary, all of this. For example, I'll take an example, the simplest one, binary. Okay, you can have uh, binary instructions that use this format, the binary format, which means binary instructions are something like add, subtract, etc. They require, in, let's say if you're using the RISC-V case, which is what I'm working on, you would have three registers. You'd have two registers as operands, and then the resultant result will be stored in the third register. So you have two registers for the, let's say, an add operation. You add both values, assuming that both of those values are in two registers, and then you put the result of that in the third register, right? So that's kind of what this is. This is an instruction format. And then that instruction format, multiple instructions will conform to that format. And this is true for pretty much every architecture that you can think of. That's kind of why Cranelift is an IR, right? This is the instruction formats available in Cranelift IR for you. So you use instruction format and instruction data together, as you can see. This opcode can simply be the add opcode, the subtract opcode, the divide, multiply, whatever. It takes two values, right? So that's the instruction format and instruction data. And then there's this thing called the context. We sort of looked at that when we were talking about ISLE. So I'll basically talk about what I've understood. So if we were looking at source and we were looking at ISA and let's say RISC-V, yeah, over here, this is pretty much, you remember we talked about that context trait implementation when we we're talking about the domain-specific language in Cranelift called ISLE? That context, the type that implements the context is called, the ISLE context. And for a particular target, you have a context. So that's RISC-V 32 ISLE context. So that is what this type is. And it'd be very useful for you to sort of get a hang of things, because what it does is it actually wraps a backend, which we've already discussed, but I'll repeat this again, and the type of instructions that are produced, because each architecture is obviously going to have different instructions. So file context actually has two types that it wraps, which is one is the I generic and the B generic. Both of them are, this is target specific. Both of them are target specific. That's what it means. So yeah, as you can see, in my case, I'm doing this for RISC-V 32. So you'll have a RISC-V 32 backend. And the type of instructions that RISC-V 32 produces, I'm just calling them machine instructions, which is this one, right? So yeah, that's this. And yeah, and if you want to learn more, you can actually go look at the previous two videos. And then the last one is Cranelift Backends. This is going to be a rehash. We looked at this the first stream. We'll talk about this again. This one is basically, so the way you start off when you talk about building a backend is Cranelift, CodeGen. You don't look at anything, you just jump into ISA, which is instruction sets. You'll find all of them. So all of these things are actually backends. And the one that I'm building is RISC-V 32. And it's going to be standard, all right? The only important thing is that if you actually jump into the implementation for it, you will see a bunch of things over here. while everything's important, we've already discussed the fact that, this is the part that actually takes your Cranelift IR, whatever, optimized Cranelift IR, and then produces virtual register code, which is the V code. That's what this function does. Uh, and there's also another function, which I believe is used by the other code, which is, should be able to find that somewhere here. Mm, right, just give me a minute. Okay. So lower is a type that you can think of as a container for pretty much the entire lowering process that we go through. That means us going from Cranelift IR to machine instructions. Uh, this is the type that actually helps us do that. It's got pretty much everything it needs. The machine instructions that you want to build, the register allocator that you want, the function that we're going to be lowering, and then a whole bunch of other things that you need, like side effects that, if any, you want to capture them, uh, and a whole bunch of other things. I mean, it'll take a while to go through this, but this is a very important data structure again that you can look at. What I was looking for was where exactly is Ebola? Yeah, no. Yeah. Right. So RISC 532 implements the lower backend trait, and then you get these two different methods that you can use to actually do your lowering. In other words, this thing is going to use that data structure, as you can see over here, and basically perform the lowering. I walked through this as the first video, so that shouldn't be too much of a disconnect for me as well when I come back to this, because I'm only doing this whenever I have some free time, and I'm not having much of that of late. All right, so those are what I would say are sort of the interesting data structures that you would want to know about if you're thinking of building Cranelift backend. Again, I probably will do a much better, version of explaining this once the actual backend is ready. But I just thought I'd put this quick pieces together so that it's helpful for me and for anyone who's going to be working on this. So with this context in your head, here's what we can do to add a backend. So the first thing that you do is you create a folder for the backend, like so. Yeah, Cranelift, CodeGen, source, ISLE. So you create your backend folder, all right? And then you start by, if you're working with a backend that is very similar to one of these, one of the existing ones, things tend to move fast. But now that you actually have 5 of them, I think, it's pretty much going to be the same thing. You could look up the other backends and see how you'd want to do it for yours. So you create the folder, and then the first thing you do is you define the backend, implement the required traits, which I just showed you, which is the lower backend, this one, and the target ISA. So this thing needs to implement those two traits at a bare minimum, target ISA and the lower backend. Once you've done those two, then you can add your file files, which is basically all of your machine-specific instructions. That means how do you take Cranelift IR and convert them to the best possible machine instruction? That's basically these two core IL files, the instruction.il and the lower.il. That's it. Once these two are done, then you can also go ahead and you should also go ahead and implement the ABI, or the application binary interface. And in the application binary interface, what do you have? The best way to sort of show Yeah, sorry. Oh, did I just close my thing? No. Right. The best way to look at the binary interface is, over here, where you'd pretty much be able to get all the information that you need. Here's where you're going to talk about the calling convention, the, it's got a bunch of things, the machine dependencies, the function APIs that you want to use. All of that stuff is pretty much here. And this might take a while is because this is very architecture specific. And depending on how well versed you are with the architecture, you may have to spend a little more time with it. That's how I think about it. Uh, yeah, I mean, there's not much. Once that's done, then you can go ahead and add the ISO specific settings, which is what we're looking at over here. So you need these settings. This is again part of what we discussed in the previous one because there is a build script that does two things. One is ISLE is a separate language. So obviously, before I can go ahead and compile Cranelift, whatever ISLE produces as Rust code, that needs to be generated. So there's a pre-build step that needs to be performed. So apart from your macros being expanded, the ISLE code also needs to be uh, pretty much translated or converted to Rust. And the settings piece is it's where we're pulling that from. I already showed that to you, I think. So let me see if I can pull that back up. Yeah. See, this setting stuff is what you're interested in. You would be want to looking. Okay, you're not able to see this file. Let me see if I can. Yeah, see this? You have settings for each. So you'd have shared settings and common settings. Shared settings for any architecture and architecture specific settings as well. What are these settings? If you scrolled, you'll be able to find them. You're basically trying to figure out what sort of support exists for, let's say, floating point, for double precision floating point, for vector extensions, all of that stuff. Additionally, you'll also get to see this thing called descriptors, and they're very self-explanatory. You can sort of look at them. So the thing that you need to know is these flags, which is 4 bytes, which means 4 into 8, 32 bits. You're pretty much going to be using these flags to figure out how you want to go about compiling your, for which target you're going to be, exact target are you going to be compiling. That's what the settings stuff controls. Same thing in, the regular settings as well. But in the regular settings, the shared settings, you have about 80 bits, right? Because that's 10 bytes, right? Okay. Yeah. So yeah. So as you can see, you pretty much be spending a lot of time in the artifacts that are generated pre-built. Because if you're actually going to be writing this stuff needs to be first generated. Then you should be able to call your, um, do the Cranelift compilation. So you are going to be spending a lot of time. There's the documentation does tell you if you don't want to dive into the target folder and look at this, there's a way to do that. I somehow find this better. It's me. Okay, so that's one. Then what else? Yeah, then the last step is obviously you need to know that everything's actually working correctly. In order for you to do that, you need to write what are called file tests. And file tests are right here. So all of these things need to work. If this doesn't work, then there's no point. So basically, in ISA, for each architecture, you're going to have a file test. And you need to be doing this a lot because there's a lot of tests that you will need to pass. So the suggestion I think was made to me, or rather I made, and was, uh, you know, and people on the Cranelift Julep channel said it's a good idea, is start off with the smallest subset for the backend. In, let's say, RISC-V 32's case, I'm only starting with RISC-V 32, the base integer instruction set. Then you can go ahead and I'll add all the standard instructions, sorry, standard extensions, and then any other extras that you want to do. But that should be a step-by-step thing, so that it's easier to do things like that because there's way too much for you to like navigate to figure things out, especially if you don't know anything about compilers and this is the first time you're working with one. Right. Okay. So that's the backend. All right. So granted, there's no pictures. I just wanted to put this together because I've been running around like jumping through multiple files trying to figure out what's doing what. I thought I'd put this quick video together so that it's easier. Now, you don't know whether a lot of the stuff might change, the layout might change. But I think at least the foundational ones, these pieces, I'm guessing they won't. You don't never know, but so yeah. So that's kind of what I wanted to sort of talk about. Some of the design choices, some of the interesting bits, how you would get started, where you'd look for things, etc. Yeah, so far, very, very, very interesting. Okay, that's about it. Thank you.